Probando, probando audio. ¿Me escuchas, Misa? ¿Me escuchas? Hi, good morning. I wanted to thank you guys for joining us today for the webinar of Introduction to, Design and Implementation of Fiber Networks. Just give me a second. I think I'm sharing the wrong presentation. They're just very similar as I told you. Give me a second, I'll share it with you right away. Okay, now we have the correct presentation. Thanks everybody for joining. Today we're having the continuation to Intro to Fiber. I like to call it Fiber 101. Now we're looking at design. Now we're looking at design and implementation of a FTTx network. So just bear with me a second and we can start right away. Okay. So we learned last webinar about the basic concepts of fiber, what types of fiber, how to use it, limitations, pros and cons. So now that we have that information in mind, we can start learning about how do we design a fiber network. So just let me transition real quick and let's start. Okay, so As last time, we have our considerations. So we have what do we need to take into account for an FTTx network, typical network architecture, what information do we need to design a fiber network, how to calculate the fiber to use, attenuation, power calculation, and asymmetrical networks. So as I told you last time, we're going to have a little bit of math for this presentation. So designing an FTTH network. So the aspects to consider, network design must fully cover the target area. We need to prioritize high potential market area. So what does that mean? If we are looking to do fiber in an area, we have to take into account, because we're already going to do like the investment, we need to take into account our potential growth. How is the area going to grow? How many more, where can we leave like spaces where we already have fiber? So if anybody builds there or near it, we can also connect them to our network and potentially like grow our market value, grow our customer base. Avoid inefficient and repetitive installations, and the network must allow flexibility for potential growth. So whenever you're doing like a design, you always want to have extra spaces where you can grow the network. I'll teach you about that in a minute. What information is required for the design? Well, I don't know if you know this, but we do some labor here at EPCOM. We can help you with your design, so you can register your project with your sales executive, like, hey, I'm doing a school, a hotel, a suburb, and this is the information we're going to need, like number of clients or potential clients, how many people are going to be connected, how many houses, how many rooms are going to be connected to like the fiber network. The fiber optic installation environment. Is it going to be directly underground? Is it going to be over in the air? Is it going to be indoor? Is it going to be like through a tube? What services will you provide to your clients? Internet, IP telephone, IPTV, CATV, POTS. How much are you going to offer your clients on the upstream and downstream of their speed plans? And the locations of your main site and all of the branches of your network. So when you're sending, you can give us this information and we can look into it to work, or we can give you some considerations. But if you want us to work on the project with you, we provide the service, but there is a labor charge. Depends on the size of the project. Mostly it's dependent on the time it's going to take us to do the project design. So the time to develop the project depends on the size of the project and the availability of the project engineer that receives it. At the end of the project, you will receive the design, the bill of materials, and the attenuation calculation from the furthest client and the closest client to your OLT. So if you don't remember, the OLT is the optical light terminal. So basically, you connect your router to your OLT, and that's the OLT manages the fiber network. And we can organize a meeting to finalize project details, like tell you how much it's going to be, explain to you how we did the calculation, explain the materials we're going to use, and stuff like that. So just when we're in the planning phase, we need to confirm the position so we know how we're going to do the coverage and the nodes. We're dependent on this information to do like the most efficient routes from where you're going to place the OLT. So the most important node is the CO, where the OLT is going to be installed. So the CO is just a convergence node, convergence area. The plan must be done parting from this point So this is our starting point, and everything from there, we're going to see how we're going to distribute all of the NAPs and LCPs based on the first node. So the number of fiber cores are based on the trunk fiber and distribution in base of the nodes and the demands for each one. So you can see like a little, we have the node, trajectory, and the number of cores. So this is how we look into it. So the CO, where your OLT is, there are several types of architecture. So you have your main one, and then you can use a splitter to distribute. You have your splitter on the distributor, and then you have your network access points. So this one goes to 32 or 64, and then to 128. So each of these spaces is like 128, so 8 times 4, it's 32. So depending on how you do like your installation, you have your first distribution, then you have 8 distributions each, so 32 to 32 to 32, and that's how you have to look into it. We start from our CO, then we have our convergence point, and then from the convergence point, we distribute to other users. So at the end, each fiber, it's going to have a user. So you have like 128 users here, 128 users here. So at the end, we have like 32 or 64 users. So you go from your CO, you have your distribution fiber, and then you have your local convergence point where you go like through 4 points. And on this point, you distribute your 128. So you're going to have 8 users through each network access point. So let me show you how that looks. If you're looking at on the stream, this will be your local convergence point. I don't know if you can look at it. Your local convergence point. This will be placed like in the middle, on top of maybe on the ground or on top of a building. And this is your access point. Let me open it up for you. So this one's already terminated. So you have like a splitter and you have some connectors. So you can go through each one of these. These are 16 connectors. This is the, if I remember correctly, it's a FDP 420F by Fiber Home. So each one of these connectors, you can do like a run from fiber, drop fiber from here to the home. That's your final run. So you do like your LCP to your NAP, and then you connect to your NAP and go from your network access point to the house or to the building. This is how a splitter looks like. So inside of that box, there are 16 of these connectors. So at the end of the day, you have your connectors and you send them to the house. So I'm going to show you this in more detail a little bit later. It's one of the passive components of a fiber network. So this little box takes in the connectors, and then you have fiber in the home, and you can run it from there to another spot. So let's go with the next slide then. So let me close this little box. The other way. Okay, so this is the typical architecture of a fiber run. So you have your first level splitter, and from there you have like 1 to 8. You split it into 2 pieces, and you have in the building you have 8 or 4 connectors. So you split from there, and then you have you take your trunk fiber or your backbone fiber, and you connect it inside the building, and you have your splitters in each floor. So in each floor you do your second level splitting, and then at the end you go to your ONT or your ONU. or as I showed you here, this little rosette box where you can place like your fiber, and then you can use as patch cord or a patch cord to connect to your ONU. It's one of those passive components of a fiber. So how do you calculate the quantity of fiber to use? Well, for backbone and distribution fiber, add up the distances and add an extra to 10 to 15%. I'm not trying to sell you more fiber in a sleazy way. It's just a recommendation of correct practices. So if you add 10 or 15% extra fiber to your calculation, you're not worried about running low or running short. There are times where you make a mistake. So having a little bit extra helps you imagine if you just are tight and you make a mistake, and at the end of the fiber run, you're just like a meter short or 2 feet short on how much fiber you needed. So it's important to have a little bit of extra. Even when you're doing like floor installations, they do recommend you take a little bit more than you need. Whenever if you make a mistake, everybody makes mistakes. There's no shame on that. So this is just a little bit of like how to calculate with a 15% margin of error. So you just multiply your distance by 1.15, and you have like how much you need. So that would be like 2 kilometers, right? So for drop fiber, we estimate the average distance from the network access point to the home. In this case, 70 meters. So you're going to have 300 clients. You calculate 70 meters. So that's just the average distance. And at the end, you have how much how much drop fiber core you're going to have for each one of your clients. So one of the main tasks when designing a fiber optics network is to evaluate the acceptable attenuation budget. Attenuation is a bit of a resistance in your network. So we need to calculate the closest value. Like let's say the first user is like 20 meters away from the OLT. So we need to calculate that one. And we need to calculate the further one. So to do this, we take the launch power of the transmitter module. So your OLT has like a range sensitivity. So we're going to take that. We need to take fiber connections, cable, device sensitivity, and other like safety margin and potential repairs. So from that calculation, we have from your OLT, you have your first device that's an SFP SF UPC. It's a model we have from B to C++. Here in Upcom, we manage a C++++. So we take the average power of this device, in this case 3, 5, or 7, and we use it to calculate with other component loss. So you have this is your loss from your optical fiber at 1 kilometer. We also have loss with splicers. This is a splicer. I know a lot of people don't use this when starting. They're expensive devices, but they give you very low loss, very, very low. It goes from 0.08 to 1. So in contrast, a terminated connector, like a field terminated connector, gives you 0.3. A coupler gives you 0.1. And an active connector, that will be a patch cord or a pigtail, or a splitter, like a splitter connector. Well, let me show you again. So inside this little box, there are 2 couplers. So we have 2 couplers here. So this has a loss of 0.1. So you have to, when you're doing your installation, you have to count each of these devices. I have right here a UPC connector. So this is, you will consider this one as a field terminated connection. So even there's, in papers, like a 0.3 loss per connector. But if you do like not that good of an installation on this type of connectors, your loss is going to be higher. So you need to, this best case scenario, like if you have a lot of practice with these devices and you do like really good connections, the loss is going to be 0.3. But let's say this is a pigtail, like or a patch cord, like a fiber terminated. Splitters have higher loss because you're splitting like one fiber up to, this one's 8. So they are 4, 8, 16. So I'm going to show you how much we lose for each type of splitter. So this is the loss, theoretical and max loss on the splitters. So you can go see how it goes from 1 to 64. So this is a basic diagram for your connector. You have your central office patch cord, patch panel with a switch. So I put out here an Alta switch because I like it, and it has like SFP port. So you can connect your switch to your central OLT, and that goes to a mini Givik module, and you connect that. This is a fiber distribution device. Imagine as a patch panel for fiber. So you connect your SFP to your, using a patch cord, to your patch panel, and you connect that to your LCP. And then you split, you have your 128 splitter here on each one of this, and then you have from your backbone fiber, you connect all of your LCPs, and then you split them into your network access points. And each network access point has inside, like, you can have a splitter there, or you can have them pre-terminated with splitters. So you go from your main splitter to your second splitters, and then you split with your, you have it right here, you have your drop fiber. You take one of the connections and you put it in the house, and then you connect to your ONU. So let me show you so you don't get lost. So you have your OLT, well, your switch, network switch, and your home base to your OLT, then to your SFP, patch cord, distribution, and then you connect them to your LCP. And then you go from your LCP to your network access point. And from your network access point, you go with drop fiber to your ONU. I don't know if you know this. This FD500GX by CData. It has FCC. And here in the back, I don't know if you can see it, you have your PON network. So you connect your splitter, your drop fiber, you have your PON device here, and then you just take an Ethernet cable from here to your router, access point, or whatever you have in the home, and that's how you do the connection. So yeah, it's basically how you do. Or you can have this on the home. You have you take the fiber inside, then connect it to the connector, and then you can put a patch cord and connect it to whatever fiber device you have available inside the home. So that's just how you do your network. So yeah. Let's keep going. This is basically how it looks like in a basic diagram, just showing you where are the splices, where are the active connectors, where are the connector plugs, stuff like that. So if you want to do a little bit of the math, if I have a little example here, where we take our optic fiber cable, like the quantity in this case is the distance, and you just take the loss and you just do like a little table to calculate like how much loss are you going to have in your system. So taking into account the 5 dBm, where do you take, you have all of your losses here, right? So all of this is sum right here. And where do we take like this positive 5 dBm? Well, if you remember, we have it from this C module where the average power, it's 5 dBm, so that's a positive. So we take the positive 5 dBm, that's our average power of our GPON module, and you can do that with the C++ if you want to do it, or C++, it's 7 dBm. So if you're using the C++ module, it's 7 dBm. So if it was 7, it will be negative 20.02. So you take this number and you look at your GPON device and see if it's between like its sensitivity range. So in this case, for the FD500GX, the sensitivity range, it's either from, I think it's from -7 to -29. So -20, -22, it's on the range. So this would work for our little ONU here. We won't have any problems. So we talked about symmetrical networks. That was a typical network topology. Let's talk about asymmetrical networks. So in this little diagram, we're just showing you how from your local convergence point, you can have you split. You have 6 cores, 1, 2, 3, 4. I'm sorry, you have a 5-core fiber, and then you take like the last one and you have it in your box, and this is what we call fiber bleed, because you cut it there, but we're going to continue to take the fiber to the next convergence points, but this cable is no longer connected. So we take the 4th cable and so forth and so on until we make all of our connections. So how you do an asymmetrical network, it's you have an unbalanced splitter. An unbalanced splitter, it's basically you have a splitter that divides one fiber into 2, and you send like, there are different kinds of splitters. You have 5 to 95, 10 to 90, 15 to 85, 20 to 80, that type of splitting, but you don't really break the chain here. You can do like unbalanced splitter here, continue with your network, and then split the cable again further down the line. So this is the loss on the asymmetrical splitter. So you have your insertions loss, and you go like output 1 and output 2, and you have like it loses between this and this, and lose into that. So an unbalanced splitter just have like, it's basically like a normal splitter, but it goes from 1 to 2, and it splits 1 to 2 and 5 to 95 without connectors. So this is how an asymmetrical network looks like in practice. So you can see like on the image how much loss it's going to generate us. So this 14 right here comes from the average loss on the worst case scenario. So there it's a little bit more tricky because we have to calculate a little more of the fiber loss whenever we do a split. So one of the downsides of asymmetrical network splitting is we cannot give like CATV to our customers. So if we're if we're planning on using asymmetrical networks, but also planning on doing CATV to our, giving CATV to our users, it's not gonna be possible with this type of connectors. We need to do a symmetrical network. All right, that will be all for today. Thank you very much for joining us. If you have any questions, please share them with us. If there are no more questions, thanks for joining us. Hope you learned something today. If you want to send me a question, you don't want to put it in the chat, you can send it to ricardo.flores@epcom.net, or you can call and ask for me, and we can start talking about your fiber needs.